Welcome to chemistry class. We are going to look at modern atomic theory. We have been able to look at Dalton's atomic theory, J.J. Thomson cathode ray tube experiment, and Rutherford alpha scattering experiment. Today, we are going to look at the last of it all, which is Bohr's planetary theory of atom. Before we would dive into this atomic theory, we will do a recap of what we have studied so far. Let us look at what we will be doing in the course of this presentation or this lesson. In the course of this lesson, these are the various areas or sections in which we will be looking at. So first of all, we will be looking at the introduction to Bohr's planetary theory. Then we will end the lesson by answering some questions and also solving some assignments. Please note that you are supposed to solve all questions given to you as exercise or homework, and you present them when you are coming to school. This lesson, our main objective is to state the main postulate of the model, which is the Bohr's planetary theory of the atom. And we are going to apply or explain the significance of the quantum numbers in relation to electronic structure of the atom. So I want you all to pay much attention so that we can be able to achieve this goal of our lesson. Dive into the main lesson. Let's do a recap of what we have studied so far. We are going to look at the first one that we have here, which is the Rutherford alpha scattering experiment. In this experiment, we all remember that the experiment was carried out using alpha radiation or alpha particle, and the particles were used to pass through a thin gold sheet or foil, and observations were made. So we can see the observation that we analyzed when we had our face-to-face lessons at school. So there is a straight short dashes line being used here to indicate that most of the alpha particles pass through the thin gold sheet without being deflected. We are also seeing this blue arrow telling us that some of the alpha particles deflected, and they deflected at a small angle. So we can see the angle here. And some of the alpha particles also bounce back at a very large angle. So this is what we can see here. And we have interpreted all those observations during our face-to-face. So I believe you don't have any problem here. That we did during our face-to-face encounter was the J.J. Thomson cathode ray tube experiment. So we can see the discharge tube as we have the same thing in our learning material, and this is the same thing here. So the cathode ray tube look like this. We can also present it in this way, where cathode rays were coming out from the cathode which was used, that is the negative plate, and when it reaches the positive plate, we saw that since we are on like charges attract, most of the cathode rays were moving towards the positive direction. So that's what we can see here. And whenever it hits the zinc fluoride screen, that is the fluorescent screen, we see it as a glow. So that is all what we did concerning the J.J. Thomson cathode ray tube experiment. And this experiment helped us to identify the electrons. We have done so far. We can say that the work of the earlier atomic theories were used to correct the previous ones. That is, the work of J.J. Thomson helped us to correct the works of Dalton. For instance, Dalton stated that atom is the smallest indivisible particle of an element, whereas the work of J.J. Thomson made us to understand that atom can further be broken down to obtain particles like electrons. So this idea tells us that the work of Bohr planetary theory will help us to correct some of the things that Rutherford's experiment could not explain, or the Rutherford's nuclear model of the atom could not tell us. The Bohr's planetary theory was proposed by a scientist called Niels Bohr in the year 1913. This work was done to refine the earlier model to explain how electrons occupy specific spaces around a nucleus. The theory is often called planetary model because it describes electrons revolving around a positively charged nucleus in fixed or circular path, much like planets orbiting the sun. So, from the explanation or the observation of Nebo, he was using the structure of the atom to compare that of how our planet moves around the sun. So the electrons in here are behaving as the planet, and the nucleus will behave as the sun. In the course of the lesson, we are going to learn a lot concerning what Nebo did. Model of the atom. We learned that the model introduced the concept of a small positively charged nucleus in the center of the atom, surrounded by a negatively charged electrons. Though what Rutherford did looks similar to the work of Bohr, but Rutherford couldn't tell us whether the electrons moving around the nucleus were going to move with a particular energy, or he couldn't explain to us whether the electrons were going to be stable on their specific energy level. So according to classical physics, we got to know that as objects move in their circular path, they lose energy. And when they lose energy, they spiral into their moving path. That is, they enter into their center and they will cause the object to collapse. So, for instance, we can see that in the object that we have here, if these are our electrons, as they are moving around this circular path, with time they will lose energy, and when they lose energy, they will fall into the center. So if it is like that, for instance, the planet, if the earth are moving around the sun, it means that with time the earth will lose the energy to move around the sun, and the earth will enter the sun. So with regard to the work of Rutherford, that's why it was trying to say. So that was the weakness of the Rutherford's work. So we can see from our slide here is that Bohr's model was created to solve two major problems found in Ernest Rutherford's earlier nuclear model. One was atomic stability. Rutherford's model or nuclear model couldn't tell us how stable the electron is going to be within the atom. So according to classical physics, a charged electron in motion should constantly radiate energy, that is, give off energy, lose speed, and eventually spiral into what? The nucleus, causing the atom to what? Collapse. So this is the actual problem about Rutherford's work, and Bohr is going to correct this error here. Another thing is that Rutherford could not explain why elements like hydrogen emit light only at certain or specific wavelength rather than continuous rainbow. Now, in the course of our study, we shall look more into this. That is, we'll be doing line spectra and continuous spectra. Now, we are going to learn something like hydrogen emission spectra. The work of Bohr is based on the hydrogen emission spectra. Hydrogen emission spectra. When we talk about spectra, it means the emission of radiation, emission of light. That's what we mean. So we will look more into it when we are moving on with the other sections that we have. So these were the two major problems that Rutherford's work could not account for. Therefore, Bohr's planetary theory came in to solve this issue. So Bohr showed these lines represent electrons jumping between fixed energy levels. Don't worry for now if you don't get what we are doing, but when you move on with the other sections, we will be able to understand what we are trying to say here. So having these two problems in mind, let's see how Bohr is going to help us to solve it. Let's look at the postulate of the Bohr's planetary theory of the atom. The first postulate states that electrons move around the nucleus in a specific path called shells or orbits. So the other postulates include the electron can exist only in certain allowed orbits which correspond to specific energy level. Now I would like you to go through all the postulates. We will explain in our next slide. I have a diagram there and I will use the slide to explain everything there. So let's move on and look at the next slide concerning the explanation of all the postulates stated here. So please take note of it. I use this diagram to explain the postulates we just saw. So from the first postulate, it says that electrons move in circular path called shell. So this is our electron and this is the circular path in which they move. So let's take note of it. And from even what we have learned so far back in JHS, we got to know that the shells are labeled as K, L, M, N, and so on in that order. And you also know that from the nucleus upwards, the energy of the shells will be increasing. So even you can even use the size to make reference to that. So you can see that as you keep on drawing the circle from the nucleus, the size of the circle becomes big, and that one corresponds to the energy of the shell. So the first shell has a greater energy compared to the second shell and the next shell as it has been arranged over here. So please let's take note of that. And the second postulate also tells us that the electrons are allowed in certain allowed orbit. They are allowed in certain allowed orbit, or they exist in certain allowed orbit. So it means that there's no where or possible way in which electron will be at the center here. No electron can be in between this place. That's why this arrow is trying to tell us that no electron can exist here. They are all in certain allowed state, certain allowed state. And the third postulate tell us that whilst electrons are moving in this circular orbit, they do not radiate energy, meaning that with the energy that an electron has within its particular state, it will not lose the energy. So if this is where the electron was, if it is where it has been, or this is where the electron is, um, then it means that this electron, which is at energy level 2 with the energy E2, it will never lose the energy. It will be as where it is. It will be at where it is. So this is what we are trying to say here. So this one explains to us the problem concerning Rutherford nuclear model that it couldn't solve. So here, from Rutherford's model, it couldn't tell us that the electron will not lose the energy within their allowed state. So for Rutherford model, classical physics, which is trying to tell us that when you have a charged object, or when you have electrons moving in a circular path, they will be losing energy. And when they lose energy, they will fall from where they are and come to the next energy level. And the same thing, they will lose energy and they will fall into the nucleus. And since we are having negatively charged particle here and here is positive, it means that when they should fall here, they will cancel each other. And it means that we have nothing existing. And the whole atom will collapse. So that's what Rutherford couldn't explain. Therefore, Bohr is trying to tell us that the electrons are not going to lose energy. So they are going to be at where they are. Okay. Now, the next postulate, let's move it to this side. If whenever you have electron in a particular energy level, let's say here, we are saying that this electron can jump to this side. Now, let's note here. In the first one, we were saying that when they are in their allowed orbit, that is where they are supposed to be. If they are there, they do not lose energy. However, when an electron is in its allowed orbit, always when they are in their allowed orbit, we say that they are in their ground state. And the ground state is the state at which the electrons are having the lowest energy. So always in their ground state, they have their lowest energy. So all these electrons here are in their ground state. All these electrons are in their ground state. So they are in their ground state. And they said that the electrons can absorb. That is, they can absorb photons. I said photons are particles of light. So it means indirectly they are absorbing what? Radiation. Radiation in the form of what? Wave. So in the form of the light that you have in the house. So it means that the electron has what? Absorbed energy in the form of what? Photons. And when they absorb, what happens is that they become happy, and we say that they have excite. So they move from the lower level and go to higher level, or they move from the ground state to what we call excited state. So where the electron is now is what you call excited state. The question is, why is the electron not going to this level but is going to this level? When they absorb energy, they go to the level that corresponds to the energy that they absorb. So let's say if you are going to buy food, you buy according to what you have. You don't buy according to what you don't have. So here the electron is moving to this level based on the energy that it has absorbed. So it means that that energy is equivalent to this energy level. If it absorbs energy which is equivalent to this level, it will move to that place. So let's take note of that. So therefore, let's make reference to the fourth postulate. So from the fourth postulate, it says that the energy of the emitted radiation. So you can see that after this electron gains the electron, after this electron gains the radiation to move from its energy state of E1 to E2. Now it is unstable here. So that is after it go to the excited state, it want to come back because it is unstable there. That is not its permanent place. That's not its lowest energy level. So what will happen here is that at the excited state, it is going to come back to the initial state. That is the lowest energy level. That is the ground state. So when it is coming back, it will lose energy in a form of what? Radiation. It's going to lose energy in a form of radiation. So it will lose the energy that gave it the ability to come to this excited state. So the process of losing the energy to come back to the ground state is what we term as de-excitation. De-excitation. And the photon that it has released, we call this process as what? Emission. So since it has released this photon, we are saying that it has undergo what? Emission. So this photon normally is going to exhibit colors. So when we are doing spectral lines, that is the continuous spectra and the line spectra, we will get to know more about this photon or this radiation it has released. Normally it's going to show certain colors based on the wavelength or frequency at which it is releasing this photon. And when we do our next topic, you understand it more about the color that it is showing. So we are saying that here, electron in the excited state losing the energy, the photon is emitted and energy will decrease. So it will go back to the its original ground state. And to find the energy that it released, so let's say here is E2, we will say that the difference in terms of the energy release, difference in terms of the energy release, if you want to find the energy of the photon release, is going to be the difference of where it was, that is the highest energy level, which is E2. So E2 minus where it is coming, which is the E1, and that will give you the change in energy, the change in energy. So take note of that one. And that was what the postulate was trying to say in the postulate number 4. Now, with the feed postulate, it says that the size of the orbit and the energy of the electrons are related, meaning that the size of the orbit, which corresponds to the energy of the orbit. So if I'm having a bigger size, it means that electron too is having a bigger energy. So for instance, among these shells that we have indicated here, if an electron is here, or this electron as it is here, it is the one that is going to have the highest energy, because the orbit in which this electron is found is very big. So the size of the orbit and the energy of the electrons are related. Then lastly, the last postulate states that electron can only make transition between energy levels that correspond to specific amount of energy known as quantum. So here it says that we know that electron can only move from one energy level to the other energy level as a result of the energy absorbed or as a result of the energy emit. So that energy release, that energy absorbed is what we refer to as quantum, and quantum is specific amount of energy. That's what we are trying to say here. So it means that all the energy level here, they are quantized. Quantized means that the energy level has specific amount of energy. Each energy level, they have a specific amount of energy in the form of quantum. So when we are moving on, we'll be learning about quantum numbers. So we can tell you that, let's say the first shell, we will call it that it has a quantum number of, let's say, n is equal to 1. So it tells you that when you hear quantum, anytime you hear of quantum, it means energy. It means energy, specific amount of energy or discrete amount of energy. So take note of that. Okay, so that is about the postulate of the Bohr's atomic theory. That is the postulate. This is a diagram of the same energy levels. Here we are presenting the energy level using line. Now this one is the atomic emission spectra of hydrogen atom. The atomic emission spectra of hydrogen atom. So we can see some lines. The lines are showing the emission, that is the radiation or the photons given by the electrons within their respective energy levels. after they have undergo excitation. So the line showing that means that the electrons are now doing de-excitation, moving from energy level to certain energy level as a result of the photons that they are losing, or the energy that they are losing. So, and it represents the emission spectra. So this is what Bohr used to study the atom, and got realized that the atom can release uh, certain radiations, and this one is what we term as spectra. So the spectra, when we use line to represent it, we call it line spectra. And when with the line spectra, they are specific to certain wave length or wave number. We'll be looking at that. So here we said that in Bohr's model, electrons do not move randomly. So it means that there's nowhere you'll be finding an electron in between the levels. If they move randomly, then you can find an electron in between, but rather they move within specific allowed states. And they say that they move between specific energy levels through absorption or emission of energy. So in terms of movement, for electrons, they don't move, but the only way that will cause them to move is either they lose electron when they are in their excited state, or they absorb electron when they absorb radiation when they are in their ground state. So that is about the electrons. So here we are saying that every energy level in an atom are discrete, meaning that they have specific values and are not continuous. So please note that statement, write it down and underline. And they are not what continuous. So they have specific value in terms of their energy levels, and the electron must exist in what their allowed state. The electron, they must exist in their allowed state. So you can see that here the lines of the energy levels are getting very close. So when the moment you are moving away, now this place that you see here becomes our, after, before this line, we are using this place to represent the nucleus. So this is the first shell, the second shell, the next shell, and the rest. So as we are moving away from the nucleus, the lines begins to come closer. They will be coming closer and closer and closer. And when they behave that way, we have a term that we give it to it, and it means that they are, what we are saying, that they are what, there's a convergency, like convergent radiation. There's a convergency. So as you move further from the nucleus, the gaps between the energy levels decrease or converge. They decrease. So let's note that. And we are saying that whenever we have an atom where the electron gains energy and they leave the shell, or they leave their orbit and move away from the shell, we call that process as ionization. So ionization occurs if electron absorb enough energy to reach the infinite level. That is, they leave their allow state and go to a level which we cannot even account for where they are going to exist. It means that the atom is undergoing ionization. So let's take note about that one. um Movement of the electron. So the electron moving between energy levels. So the electron undergo two movements, moving up and moving down. And when they move up, we say excitation. When they move down, we say de-excitation. And at that point, there's emission. When they move up, there's absorption. So let's take note of that. Okay. So say when an electron gains or absorbs energy, it moves from a lower energy level, that is a ground state, to a higher energy level, excited state. When an electron relaxes and falls from the higher level back to the lower level, it loses or emits energy. This lost energy is released as photon of light. photon of light. So this is what they are being used to show us the photon of light. This image is an example of different atoms in which um, the electrons in there have gained energy. So we study the electron gaining energy at different wavelengths. So these things that you are seeing, the reason why we are seeing different colors is because of the different frequency or wavelength at which we are studying the emission of the the electrons. So when we are doing continuous spectrum, we will show you or we will look at rare pictures of that, where you will see different atoms and where they show their wavelength. And you can see that the each if we take this one to be hydrogen and let's say this one to be sodium, you can see that at different range, depending on the range or depending on the wavelength at which we place the atom, we are going to see a different color. So we can use this one to even predict if, let's say, you have a sample, you want to know if it is sodium or hydrogen. We can use these um, spectral lines, or we can use these emissions to determine that atom, because we can see that, for instance, this atom, we don't know this atom, but if you should place this atom within the electromagnetic spectrum, we don't worry, we will be looking at the electromagnetic spectrum. So let's say if the range here is, let's say, 1,000, and we present 1,000 for all of them, for this atom at 1,000, the electron cannot undergo any emission. The electron cannot undergo any emission. But for this one, they undergo emission. So let's say if you are studying them, you can use this one to predict that this atom is not this atom, because at this range, they don't give out what emission. So that is that about the emission spectra. And is as a result of the energy levels or the energy at which their electrons require in order for them to translate or transition from one energy level to the other. So let's take note of that. We have come to almost the end of the lesson, but like as we realized in our previous study on the other theories, we got to know that after their discoveries, there were limitations. So the same thing applies here. Now, one of the limitations of the Bohr's planetary theory of the atom is that the Bohr's model works only for single electron species. I informed you that the Bohr's model was based on the study of the atomic emission spectra of hydrogen atom. That is the emission spectra of hydrogen atom. That Bohr was studying how hydrogen atom emits what? Radiation or photons. So he based his work on that. He did not apply to other atoms which have more than one electrons. So for complex atom, Bohr didn't was not able to tell us how the emission was, or how the electrons in there also emit radiation. So that was a weakness of his model. Then the Bohr's model too made us to understand that the electrons are within their fixed state, that is within their allowed state. He said that they are fixed there, meaning that whenever we go to that allowed state, we should be able to find the exact place that the electron will be. But however, the further work of Heisenberg made us to understand that we can never determine the movement and also the position of a particle at the same time. So for instance, if we are moving, we cannot tell our position in the course of our movement, and we cannot tell our movement in the course of our position. So if we stand there, we can say that we are moving at this point. If we are standing, we can't tell. So that's what Heisenberg was trying to say. So according to Heisenberg, he said that we cannot determine the exact position and the movement of a particle within their allowed state. So these things account for the weaknesses of the Bohr's model. We shall look at some few questions to assess ourselves on what we have done so far. So the question is, we are to state three major postulates of the Bohr's atomic theory, or of the Bohr's planetary theory of the atom. So right now, take your pen and your exercise book and state three major postulate of the Bohr's planetary theory of the atom we have studied so far. You have 1 minute to do that, and I believe all of you can do it. So, in the course of our lesson, we were able to know that according to the Bohr's theory, the main postulates were: electrons move around the nucleus in a specific path called shells or orbit. The electrons can exist only in certain allowed orbits, which correspond to specific energy level. And lastly, while an electron is in a particular energy level, it does not radiate energy. Bohr's atomic theory is very, very interesting, and it has made us to understand a lot of things that is ongoing right now. So in our next lesson, we'll be looking at the spectra I was telling you, or I was mentioning them in the course of the lesson. So we will look at the spectra and we will learn a lot about it in reference to what we have done today. So I will entreat you that kindly write down the notes in this lesson, and anything important that I said, put it down so that you can use it as a form of revision. Get your learning material too and use it to adapt to what we have done so far. I wish you the best of all. And after this question, the next slide is going to be our exercise. Kindly look at the exercise and answer the questions based on what you have learned today, and make sure you bring the exercise book for your recording or for your continuous assessment. I wish you the best. Stay safe. Bye bye.